name is Herbert. Today I will be talking about FLEdge, benchmarking federated machine learning applications in edge computing systems. So this is a work that's currently in submission, and a paper preprint is already available on arXiv. So before we get to it, a few words about myself. So my name is Herbert. I'm a research associate at the Technical University of Munich. My research focus is federated machine learning systems in resource-constrained environments, i.e. edge computing systems. Furthermore, I'm working on an industry project that deals with federated non-invasive condition monitoring for industrial processes. And I'm also responsible for managing our 2000+ CPU core private cloud, including some GPU servers and an entire edge computing testbed. So at the beginning, I want to introduce federated learning very briefly. Why do we need privacy-preserving machine learning? Well, first of all, if we think about machine learning in general, what we do is we first of all collect data in a central place. We pre-process it in that central place, and only then we train our machine learning model. However, this comes with a lot of privacy related challenges, especially when we think about systems where we have many users, each holding very little data. So for instance, hospitals or people owning a car, right? And there we often have the problem that we can't get the data from the users, so we can't train our machine learning. What can we do against it? Well, in 2017, federated learning was introduced with a technique called federated averaging. This is what I will explain on this slide. So first of all, we as machine learning engineers, we design our model that we want to train. And in federated learning, we now don't train it ourselves, but we put it on a server. And we allow clients, so the users, to register. And each client holds very little data that can be used to train that global model. So the server sends an update to the user, sends a model to the user. The user does all the training on their local device, and only then the user sends back an update to the server. Once every user that was selected for training run has done that, these model updates are being aggregated into a global model, i.e. our model we initially developed is getting updated with trained weights. And one very popular technique is federated averaging, basically where we would average every single model weight with among the client updates. And we repeat this over multiple rounds, because through this round-based mechanism, we achieve model convergence and a very competitive training progress as compared to central machine learning as we know it. So today, I want to talk about FLEdge. FLEdge deals with 4 major points. Number 1 is resource heterogeneity. Number 2 is energy efficiency. 3, client reliability, and 4, data privacy. In this short talk, we will be focusing on resource heterogeneity and energy efficiency. And I will briefly discuss our key insights. So first of all, when we think about hardware heterogeneity, what we see here is the time it takes for a certain device type to process one batch of data in a deep learning model. We also evaluated various model architectures, and what you see in brackets is the number of parameters a model has. And what is noteworthy is that with increasing model size, we see a exponential growth in processing times, especially on embedded devices, which are the Raspberry Pis here. We also have another type of embedded devices, the nanos. So these are NVIDIA Jetson nanos with 128 GPU cores. And what we see is their runtime still increases, but not exponentially, which suggests their ability to handle a lot more complex deep learning models than the Raspberry Pis. What we find in our experiments is that the hardware acceleration on the nanos speeds up the training process by 16 times. And what you see here are state-of-the-art federated learning workloads. Yeah. So we see the importance of adding hardware acceleration to embedded devices. And one further topic that goes very closely along with that is energy efficiency. Here we again have the same x-axis and a different y-axis. Here we now measure energy efficiency as samples per second per watt power draw. So basically, how many samples can we process when consuming 1 watt of power? And what we see here is we can process 96 samples per second per watt power draw on the nanos, while only 33 on the GPU. In total, the GPU can draw up to 300 watts, so it is much faster than the nano, while the nano can only draw 15 watts. But still, we see in terms of energy efficiency, the nano is 3 times more efficient. And when comparing the nano embedded device against the Raspberry embedded device, we see it there's also almost 4 times, the nanos are 4 times more energy efficient. So what we want to express with that is that energy efficiency plays an integral role in federated learning research, but the way it is done today mostly addresses new methods and sort of better aggregation techniques, but neglects the fact that energy efficiency or the workloads that we train with are better suited for embedded settings. And this can help us reduce energy consumption by a lot. So that was a quick overview of the first 2 main results in our paper. To conclude, what do we learn about resource heterogeneity? So resource heterogeneity has a 16 times performance impact when comparing different embedded device types. When we transfer that into the real world, we need to consider that many applications are bound to industrial processes. So evaluations must consider these industrial processes, and they are often characterized by very long life cycles and that they contain legacy devices, so without hardware acceleration. And therefore, we need to include these legacy devices, such as Raspberry Pis, in our evaluations for federated learning workloads. Secondly, energy efficiency. Well, we show that hardware accelerated embedded devices are consistently a lot more faster than non-hardware accelerated embedded devices. And therefore, also with sustainability in mind, we need to consider the evaluation of federated learning workloads on embedded devices. So this was a very brief talk. If you're interested in more details, please have a look at our preprint. I'm very much looking forward to feedback, and otherwise, always happy to answer emails. Thank you.